Hi, everybody. This is Mr. Karlovsky, and we're going to work through our notes from section 6.4, part A. And we're going to dive right in with a bunch of examples. You can see this first example here. It says, given that capital F of x is the integral from 0 to x of t squared plus t dt. And right at the part it says evaluate the integral. Now, sometimes we think evaluate means that you're going to get an actual value, but I guess what we mean here is, hey, let's perform the integral by using the antiderivative. So, boy, how do we take the antiderivative of t squared? That would be 1/3 t cubed, and then the antiderivative of t, 1/2 t squared, and then we know that if they were numbers, we would evaluate them from a to b. Well, in this case, we're evaluating from 0 to x. Okay, well, the procedure here is we're going to substitute in x, so 1/3 x cubed plus 1/2 x squared, and then minus, and I know that substituting 0 here seems a little trivial, and it is, but we're going to make sure we always think about that step. That's how we would evaluate. And so in the end, what can we simplify? Well, we know that this whole part here on the right, 0, 0, that's just 0. So in the end, that f of x that was given could just as easily have been written as 1/3 x cubed plus 1/2 x squared. All right, so that's capital F of x, just written in a different way. All right, so now if you come over here to part B, it says, hey, let's find f prime. Okay, let's take the derivative of this f that we just reevaluated. All right, well, the derivative, if we just use power rule, well, 1/3 x cubed, if I take the derivative, that would be x squared, and plus 1/2 x squared, take the derivative, that would just be x. And we get a very kind of conclusion. And notice that here, instead of prime, we use the ddx notation. So it turns out the derivative of the given integral from 0 to x of t squared plus t dt is just x squared plus x. And that's really what we're going to do here. We're going to develop a few examples and just hopefully make a conclusion. And that one, if you just look at it just from a patterning perspective, you might think that you already kind of have it figured out. And let's see if we do. Example number 2. New function here, f of x is the integral from 1 to x. So that's a difference. The previous one was from 0 to x. Let's see what this is from 1 to x of a new function. Of course, the square root of t is, t to the 1/2 there. All right, so let's evaluate big F of x. All right, so big F, here we would take the antiderivative of t to the third, 1/4 t to the fourth. And then, are you getting better at this here? The antiderivative of t to the 1/2, well, that's t to the 3/2. And then what would the coefficient have to be? That would have to be 2/3 to cancel it out, right? All right, so we're going to evaluate that from 1 to x. All right, let's see where this goes. Again, we're just developing a pattern here. Let's see where this takes us. 1/4 x to the fourth and 2/3 x to the 3/2 minus, and all right, now at least substituting 1, we're going to have probably not 0 here. Let's see what we get. So I'm slowly substituting in 1. All right, so as I simplify this, all right, I've got 1/4 x to the fourth plus 2/3 x to the 3/2. And now at least this part is not 0. There is an actual value there, right? So that would be 1 plus 2/3, and but that's minus, so I'll do those fractions for you. I don't know why that keeps happening to me. Let's do the fractions. That's minus 5/3. Okay, so there's not a 0 at the end. All right, well, hey, that's big F of x. Again, notice that's all we're doing is just rewriting f of x in a different form than what was given to us. And then we are taking the derivative, f prime, and let's see what happens. Well, the derivative of 1/4 x to the fourth is x to the third. Derivative of 2/3 x to the 3/2, well, that would be 1, and then subtract, oh, that's x to the 1/2. And I'm going to leave it as x to the 1/2. I know that's the square root of x. And then we know that the derivative of this constant is always going to be 0. And that's going to be an important part here, is that Yeah, no matter what number we get there, if we then take the derivative, it'll become 0. All right, so what's our conclusion? All right, apparently the derivative of 1 to x of this expression is x cubed plus x to the 1/2. So do you see a pattern here? I would say one observation is that it appeared to not make a difference whether it was a 1 to x or a 0 to x. And that's an interesting thing. We'll see if that pattern continues. And now here comes the third example, right? Classic 1, 2, 3. Let's see where the third one takes us. New function. Now, ooh, look at this. A big difference here. Okay, so like I said, we're doing from 3, all right, new number at the bottom. And now we're not evaluating just to x, but rather to an expression of x, in this case, x squared. All right, let's see what happens, okay? So let's get my purple pen here. All right, so let's evaluate using the antiderivative. Well, whose derivative is cosine of t? That would be sine of t. All right, so that's the antiderivative. And now, if we're evaluating this from 3 to x squared, okay, well, that would be the sine of x squared minus the sine of 3, right? That's just the number 3, and then the sine of 3. All right, so in this case, really nothing to simplify. I'm just going to get rid of those parentheses. We really don't need those. So this is the sine of x squared minus the sine of 3. And that's f of x written in a different way. Notice we're doing the same process for every problem. Okay, so where do we go? Hey, let's take the derivative. And now I'm going to use my slow, do you see what's about to happen voice. All right, so let's take the derivative. Well, what's the derivative of sine of x squared? All right, hopefully it hasn't been too long for you to remember that, oh, the derivative of sine is cosine. And then we had this little thing called the chain rule that, oh, the chain rule times x squared, or I'm sorry, times the derivative of x squared is times 2x. And then we have the same thing that sine of 3, please do not write that the derivative of that is cosine of 3. Sine of 3 is just a number, so its derivative is 0. Bye-bye, it's gone. And so, classic, we thought the pattern was pretty obvious, but turns out there's something just a little bit extra in this third example of how we got there. All right, and so do you see it? Do you see what happened here? What we're trying to develop here, and we're just going to kind of summarize before I go to the next page. What we're trying to see is that basically we had a function that was defined with an integral, and then we took the derivative of that function, and what we see is that in the end we pretty much get the exact same thing, right? I mean, for our three examples, here we had the derivative of the integral of t squared plus t, and we got x squared plus x. Okay, it's pretty much the same thing. The second example, t cubed plus square root of t, we got x cubed plus square root of x. Pretty much the same thing, where the bottom number did not matter. The third example, we're going to have to make sure we process this. What happened here, yeah, it is just the cosine of that x squared, but then that 2x we need to make sure we are always thinking of. So what this develops, and again, it's just through three examples, is called the Fundamental Theorem of Calculus, Part 2. Part 1 was kind of what we did, where it allowed us to take the antiderivative and evaluate the top and bottom bounds. So please, let's just read this really carefully. So here's an important thing. It says if f is a continuous function, that is an important aspect here. F is continuous on an interval from a to b. And if a function is defined as the integral from a constant, notice this is a constant on the bottom, a, and x of f of t dt, well, then the derivative is just f of x. And that's it. It looks so simple, right? For something called the fundamental theorem of calculus, it really is kind of very simple, where the concept is, hey, the derivative of an integral, I'm not going to say they cancel out, but they kind of undo each other in a sense, right? Where f of t, the derivative, is then just little f of x. Okay. However, the note below, if we read this really carefully, it says if the upper bound is a function of x, and I said function of x, or just basically an expression where it's not just x. then we need to apply the chain rule. Just like any other derivative, hey, if it's x, the derivative is simple. But if it's anything else, we have that chain rule derivative. So what this second expression just says is like, suppose the upper bound was some other function g of x. Well, then the pattern continues where we just substitute in g of x into the little f function. But then the chain rule means we have to then do times the derivative of that upper bound. Okay, I don't know, for some reason, maybe this is how I learned it when I was in high school, is I always called this the plug and chain. I know we don't love shortcuts, everybody, but still, just the idea that when you have the derivative of that integral, you substitute or plug in that upper bound into the function, and then times the chain rule of that upper bound as you do it. Okay, so again, I know there's a lot of notation, so hey, how do we find out whether we understand this or not? Let's do some examples. So it says use the FTC, the fundamental theorem, and other integral properties to find f prime of x for each function below. All right, well, so according to our pattern, so what you want to assess right when you're beginning is, first off, is the bottom number just a number, which in this case it is just 0. And in this one, the top expression is just x. So this problem is super, super direct. There's almost nothing to do that the f prime of x, well, if all we do is substitute in that x, then we would have the sine of x over x. And that's it. Now, if you want to always remember, plug and chain, well, what's the chain rule of x? Well, that'd just be times 1. So, we are consistent that it is the substitution and the chain rule of times x. All right, let's look at letter B again. And so you see, there was no extra work there for 4a. All right, for B, the integral from pi to x of e to the negative t squared dt. Again, I look and I say, all right, well, the lower bound is just a number. I put pi just to be silly, right? It's just a number. And then x, right, just a normal x. So again, there's nothing special or worrisome about this problem. So the derivative of this, well, we're just going to, again, substitute in. So e to the negative x squared. And again, the chain rule would just be times 1. So we are done. All right, well, they're not all that easy. Let's look at C and D. All right, we've got the integral from cosine of x to 2 of 1 over t dt. So a couple things. All right, so first off, wait, the form, right? This is why we learn the form. The form is from a to x, right? From a to x, or a to the function. So that's all right. This is why I said let's use some integral properties. Well, we can just, using integral properties, say, hey, we are allowed to reverse the bounds from 2 to cosine of x. And what's the consequence of reversing the bounds? Is that the integral is now the opposite. So in this case, there's a negative out front. That's all. All right, so now there's a negative out front. My lower bound is a number. All right, my upper bound is a expression or function. So let's see where this takes us. F prime of x. All right, so the negative is still there, right, because untouched. All right, so if we think about the silly little plug-in chain, well, the substitution part would be 1 over cosine x. And then the chain rule would be times, well, what's the chain rule? What's the derivative of that upper bound cosine x? That is negative sine x. And, that is the answer. This one's kind of interesting to me, just that, hey, if we did simplify that, well, the two negatives would, cancel. And then, hey, we would just have sine over cosine. Remember what that is? It's tangent. Again, I'm not sure we would force you to simplify like that, but I think that's just kind of a neat little extra step here. Okay, and then we're going to continue with letter D and problem number 5. Okay, and now finally for letter D. All right, something special here. We don't have a number as the lower bound, and we don't have a number as the upper bound. So this cannot even be reversed like in letter C. So what can we do? Well, again, using our integral properties. This is one that maybe you didn't quite use as often as some of the other properties, is that if I need from x to x squared, one property I could use is I could use a constant. In this case, I'll use 0. But I could just say, hey, well, let's take the integral from 0 to x squared of 1 over 2t dt. And then, remember the property, you can subtract the integral from that same constant 0 to the original lower bound x. Okay, there were a bunch of integral properties we learned, and this was one of them, that you can split apart the integral, so to speak, with subtraction of a constant to the top bound minus a constant to the lower bound. All right, so that would be the technique here, is to use your integral properties. And now let's take the derivative, and just like any other derivative, we're going to do it kind of term by term. So as we do the derivative of this first part of the integral, all right, 0 to x squared, and we reassess. We go, okay, now we've got a bottom constant, so we don't have to worry about it. Oh, but we do have x squared, so let's do the plug and chain, as I like to say. So that'd be 1 over 2, and then substitute x squared. And then the chain rule, right? This is probably the part that kids forget the most. Hey, the chain rule of x squared would be times 2x. Minus, and then now let's take the derivative of the second term. Well, we like this one. This is the normal one. Constant on the bottom, normal x on top. And so we have 1 over 2 times x. No chain rule necessary on that second piece. Now this one, again, do we need to simplify this? No, but this one's kind of a neat one to simplify. This first part, the 2's would cancel, one of the x's would cancel, you'd get 1 over x. And then the second part is 1 over 2x. And believe it or not, what that is, well, that's basically 1 over x minus 1/2 of 1 over x. And this is equal to 1 over 2x. Again, would we make you simplify that? No. Or at least I don't think we would. But if it was a multiple choice question or something, I guess you need to be able to manipulate. And so, yeah, so there we go. There were 4 examples. Let's look at these 4 examples of direct uses. The first 2 are very direct uses of the fundamental theorem. And then this bottom one's where we had to, maybe use some integral properties, and then also be careful with the chain rule if the top bound is, something other than just x. All right, so now let's do one last application problem, but this should look pretty familiar. We've been doing this, something like this all year. Find the equation of the tangent line to the graph of f of x at x equals 1. Well, we know that anytime we take or find an equation of a tangent line, we need a point and we need a slope. So here we go. Well, it says x equals 1. So let's find f of 1. And this might look scary. Oh my gosh, f of 1. Well, that would be the integral from 2 to 2 times 1 of the cube root of t squared plus 4 dt. This takes more time to write it than it does to evaluate it. Why is this so simple and easy? Because if the integral is from 2, whoops, let's use the highlighter. If the integral is from 2 to 2, well, hopefully you remember that the integral from a number to itself, there is no area between those 2 bounds, so that's an automatic 0, right? And that's a good thing, because we would not know how to evaluate that integral by hand, at least not yet. All right, so there we go. So our point is 1, 0. All right, and again, I want to make sure I'm clear. Any integral from a number to itself is always 0. Okay. All right, so that's the point, and now the slope. And I wonder if we'll apply the fundamental theorem. Well, we need f prime of x. And so f prime, all right, again, let's just assess. We have a lower bound as a number. That's good. All right, the top bound is an expression of x. So that we're going to need to remember to do the substitution and the chain rule. So the substitution would be the cube root of parentheses 2x squared plus 4. And then, very easy to forget this, the chain rule times 2, the derivative of 2x. All right, and that's f prime of x. I could clean it up, or actually we can just go ahead and substitute in f prime of 1. All right, remember that's our value, x equals 1. So that's the cube root of, and you can show your work however you need to here, 2 squared plus 4 times 2. And what is this? The cube root of 8 times 2 Cube root of 8, of course, is 2 times 2. Hopefully we all know that. That is 4. So therefore, f prime of 1 is 4. And putting it all together like we have all year long, I know you don't have to write the y minus 0, but just that point slope form, y minus 0 equals 4, parentheses, x minus 1. Okay, so again, this is a new thing to use, this fundamental theorem, part 2, and just remember the little things like I mentioned, make sure the lower bound is a number, check that the upper bound is x, or if it's not, then we have to remember the chain rule. All right, but other than that, it's a really powerful tool that we'll be using, and hopefully it makes sense. So good luck, and take care.